Welcome to the next lecture in the series on condensed matter theory. In this video I want to talk about fractional parentage, or better said on the effect that the local atomic multiplets have on the possibility of the propagation and hopping of electrons. We've seen before that we can describe the propagation of electrons in a tight binding model. Where we have lattice sites and some hopping T between the sites, and an Hamiltonian that is then given as a sum over all lattice sites, where we create and annihilate the electrons at neighboring lattice sites. We can diagonalize this Hamiltonian by a Fourier transform, and we find then cosine 2Ta, where the lattice distance is A times the creation and annihilation of the electron with crystal momentum K. We've also discussed the one-particle Green's function of such a lattice, and this is omega minus epsilon K plus I0 plus, where epsilon K is 2 cosine Ta. Now we're going to add Coulomb interaction to our system and see how this energy momentum dispersion changes. And I do not want to discuss the case where we have a single orbital per site, which we discussed in the previous set of lectures, but I want to have a look at the case where we have multiple orbitals per site. Our Coulomb interaction is given by the local scattering, where a state with angular momentum 4 scatters to a state locally with angular momentum 1, and simultaneously a state with angular momentum 3 scatters to a state with angular momentum 2 by the exchange of an angular momentum Kn. We can look at different orders of K. And the 0th order is the monopole interaction, where you basically assume that locally your orbitals are all spherical, or you look at the spherical part of your orbitals, and therefore you just count the number of pairs of electrons that you have locally for the interaction. This is the interaction that remains when you have a single band Hubbard model. But when we have more than a single orbital local, or a shell with more than one orbital, we also have the higher multipoles, the quadrupole interaction, and K is 4, etc., up to K is equal to 2L of the atoms or the electrons involved in the shell that we're looking at. And these interactions are responsible for the term splitting, giving rise to the different atomic multiplets in your system. Those are the ones that make the splitting in the different eigenenergy states that give transition metals in glasses, so the windows in churches, these vibrant and beautiful colors. Now if you look at your interaction, then F K is 0, the monopole part is screened in a solid. We do not include just the atomic Coulomb interaction that you would calculate. That would for a transition metal be of the order of 25 electron volt, so always much bigger than your bandwidth. But you have to realize that electrons do not only interact when they're on the same site, they also interact when they are on different sites. So in a model where you only want to include local Coulomb interaction, you should first of all include the difference between the Coulomb interaction when the atoms are, or the electrons sit on the same site or on different sites. And furthermore, you have the core electrons, those not included in the model yet, or the semi-core electrons, and they form a dielectricum, and within a dielectricum your Coulomb interaction is further screened because you can polarize the medium around you. Now if you look at the higher multipoles of the Coulomb interaction, then you find that in a solid they have actually atomic-like interaction strength. And one can understand this. If you want locally a multipole, or you want to screen locally a multipole, that is much harder than screening a monopole. First of all, multiple interactions, when you look non-locally, decay faster than the monopole interaction. This is 1 over r, this is 1 over r cubed as a function of distance. And secondly, the biggest screening channels are s and p orbitals. And in order to make these higher multipoles, if you have a k equal 4, you cannot make that with a p orbital, such that you need the higher angular momenta states. And very often they are not available close to the Fermi energy. Especially because, well, you have one state, 1D state at the Fermi energy, which is the one that you explicitly consider, and then the next state with D symmetry would be the one that is one principal quantum number higher, and therefore much higher in energy. So we find that in the models that we make, we have 0, the monopole part of the Coulomb interaction is strongly reduced, with which what you find in an atom, but the multipole part is still there, and that is the one that can give you very beautiful and different physics than what you have compared to the free electron case. Now let's exemplify what can happen by a model. And I want to make a model that is as simple as possible, but still contains a lot of the physics that you want to describe. And for real materials, we should go to an open D or an open F shell. Now the number of states and multiplets that you have in open D and F shells is immediately very large. And therefore it is much simpler to go to an open P shell. Now for P shells you normally do not find the parameter range that is of interest for the physics that I want to describe. But then again, when you make a model that is not so important, we can just assume a certain parameter range. Realize that the physics that I describe is important for actinides, lanthanides and transition metal compounds, although I'm discussing here a P shell, where I just do a P instead of an F shell to reduce the number of possible states that we have to consider. And furthermore, I will look at a one-dimensional chain, again just to simplify the number of states and channels that we have to consider. So this model is purely there for simplicity. And it allows you to still describe several of the phenomena that I'm after, but the model actually only applies for systems with open D or F shell. So let's assume that U or F0 is much larger than our hopping pp sigma. And again, I do this for simplicity. Similar physics as what I describe here remains if the system is metallic, but when the system is metallic you have to average over many different configurations, whereas in the case where U is very large, you know that locally you will only have a single configuration, and that's what I'm going to use. And we assume in our model that we have 3 electrons per site. Now, when U is much larger than the hopping, the charge fluctuations are going to go to 0. So the expectation value of Ni square minus the expectation value of Ni square is going to 0. There are no local charge fluctuations. We can then look at our ground state, our local ground state. It's starting to rain here. The local ground state is the state with half filling. So we have an angular momentum that is 0. We have 3 electrons, such that S is 3/2, and therefore also J is 3/2, L is 0, Lz is 0, S is 3/2. And then of course we have the 4 possible values of Sz. So we have locally 4 degenerate states. We can now also define the lattice ground state. And let's assume a magnetic field. Such that the lattice ground state wave function is given as a product state of all sides, where on each side I have the ground state atomic multiplet. And in this case Sz is minus 3/2. So we are magnetically ordered. The question that I'm going to ask for this model is, if I now add a hole to the pz orbital, then what is my dispersion of this additional hole? How will it propagate? So what I want to know is my Green's function, k of omega, where I start from this many-body wave function. I add a hole to the pz orbital with spin down, and then I want to know how this propagates through the lattice. For this, we can realize that our tight binding model, or we need the tight binding model, is a sum over the lattice sides and spins, the hopping pp sigma, a dagger p0 sigma I, where 0 now corresponds to the projection of the angular momentum on the z direction, so p0 is pz, and then a p0 sigma I plus 1 plus harmonic conjugate. So this is just our one-dimensional tight binding Hamiltonian, where one of the 3 orbitals is allowed to hop and the other 2 are not. And we assume that we're in the limit where pp sigma is small compared to f0 and f2. So it's small compared to f0, that allows you to localize your states. It's small compared to f2, such that we actually go to the lowest term of the atomic multiplet, and the other terms do not mix in. So we can now look at this wave function, or at the Green's function, and we first of all can calculate the state where we remove a p0 electron with spin down from side I, and our ground state is the 0, 0, 3/2 minus 3/2 state. And in terms of determinants, this is the removal of a p0 electron after creation of a p minus 1 with spin down, a p0 with spin down, and a p1 with spin down out of the vacuum. Well, we can commute these 2 operators, and then we're left with minus a dagger p minus 1 with spin down, a dagger p1 with spin down out of the vacuum. Now this, in order to see what the Coulomb energies is, we have to look at the possible multiplets of a p2 configuration, and this is the state with L is 1, Lz is 0, S is 1, Sz is minus 1, and this state belongs to the 3p term of a p2 configuration. And actually this is the ground state of that configuration. So if we then look, this state can now propagate. You can hop to different sites, and you will always stay in the ground state and the atomic multiplet ground state. So you will just find the dispersion you would find for a free particle. Especially we can create this electron back from our P2 state, and this is just A dagger P0 down, A dagger P minus 1 down, A dagger P1 down, which is minus 0, 0, 3/2, minus 3/2. Such that once you're in the localized state, you can just hop with your electrons from one side to the other. So our full Green's function is given as 1 over omega minus epsilon k plus I0 plus, where epsilon k is epsilon 0 plus 2 pp sigma cos Ka, and epsilon 0 is the lattice on-site energy plus the energy difference between the atomic P2, 3p term and the quartet S term that we have for the D3 configuration. So your Green's function is shifted by the Coulomb interaction, but you still have the normal dispersion. This behavior changes when the spins are not aligned, or it changes when we include things like spin-orbit coupling. So in our case, in our model so far, we removed an electron from the atomic ground state of a P3 and we arrived at the atomic ground state of a P2 configuration. But actually there is no need that removing an electron in one atomic ground state configuration brings you to the atomic ground state configuration of another, the atomic ground state term of another configuration. So let's have a look now what happens when our moments are not aligned. In this case, let's have a look at our 3 orbitals, and we have different sides, and we start with a case where we have 3 electrons on one side with spin up and 2 electrons on the other side with spin down. We now hop with 1 electron from side 1 to side 2, and we then end with 2 electrons with spin up on one side. And here we have a case where 1 electron is spin down, 1 electron is spin up, and the other electron is spin down. Now the 3 electrons with parallel spin belongs to the quartet S 3/2 term. The 2 electrons with spin down belongs to the triplet P term of the D3 and the D2, or the P3 and the P2 configuration. These are both the lowest energy states with respect to Coulomb energy. We now here have a state that belongs to the 3p term, and the question is which term does this state belong? And if this is not the atomic ground state of a D3 term, then such hopping would cost you additional energy and therefore is suppressed, especially if the multiplet energy is much larger than the hopping term. Now, in order to understand which atomic terms this state is, we can have a look at the wave function, and we first of all find that Lz of this state is equal to 0, and we see that Sz of this state is equal to -1/2. So we can now look at the possible microstates with Lz is 0 and Sz is minus a half. And there are 3 microstates. We can create our particle minus 1, 0 and 1, either with up, down, 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 up, down, or down, down, up. And I will introduce a shorthand notation where I'm just listing the spins, thinking of creating minus 1, 0 and 1 in this order with these 3 spins. So the atomic terms, we will find 3 terms, and the eigenstates are linear combinations of the 3 possible microstates. Now, if we solve for the atomic eigenstates of a P3 configuration, we did this for a D2 configuration in one of the previous videos, so I'm not going to repeat it here, but we'll find 3 different terms: the 4s, the 2d, and the 2p, the quartet S, the doublet D, and the doublet P. They have L is 0, Lz is 0, S is 3/2, Sz is minus a half. We have the L is 1, Lz is 0, a half, minus a half, and the 1, 0, a half, minus a half microstates. And we are of course interested in the complete wave function. And now I'm going to use my shorthand notation again. This is the fully symmetric linear combination. Then we have the up, down, down, minus 2, down, up, down, plus down, down, up linear combination. And the square root of a half, up, down, down, minus, down, up, up, out of the vacuum. Now they have different atomic energies due to Coulomb interaction, and the energy of the 4s is 3f0. f0 is always easy because that's the spherical part, we're just counting pairs. There are 1, 2, 3 pairs in there, so also the 2d will have an energy of 3f0, and the 2p will have an energy of 3f0, and then the ground state is reduced by 3/5 of f2, and the first excited state 6/25 f2, and the 2p has no multiple part of its Coulomb interaction. So we see that we have 3 states at 3 different energies, such that when we hop with a spin up to a side with 2 electrons with spin down, you not completely go to the atomic ground state, but you will be split over different states. Now, in order to calculate what the state actually is, we have to look at the state that we get when we create an p0 electron out of our atomic ground state with 2 electrons with opposite spins. So this is creation of a p0 up after creation of a p-1 down and a creation of a p+1 down out of the vacuum. And we can look how this projects to the eigenstates. So we have down, up, down as our linear combination, and we see that you then either go to the 2d or to the 4s. So with a prefactor of minus square root 1/3, we go to the 4s, and with a prefactor of square root of 2/3, you go to the 2d term. So this is the ground state. And this is an excited state. If we assume that Coulomb interaction is very large, we can neglect this part of the hopping such that we have an effective hopping in the case when spins are opposite of square root 1/3 pp sigma. We also have an, and I can put a plus here, I'm just changing the sign of your wave function. We also have an pp sigma effective for parallel spins, and this is given by exactly pp sigma. It was not reduced, such that we have an effective hopping for a random lattice or system where the spins are orientated randomly of 1 plus square root 1/3 divided by 2 times pp sigma. So we see that we have a system that when our spins are randomly ordered, the hopping is smaller than when the spins are ordered parallel. The fact that you can reduce your hopping by just not going to the lowest atomic multiplet is what we call fractional parentage. Fractional parentage is introduced when you build up a state in a certain configuration, so in a P3 configuration in this case, by systematically adding electrons to your system, going from P1 to P2 to P3, and you look at the overlap between the different multiplets that you have in P2 when you go to P3. And this is of course the important part that you have when you consider hopping in your model. It's important to realize that basically for all materials with open D or F shells, the local atomic multiplet energy scale is much larger than the hopping energy scale. So this fractional parentage will always reduce your hopping. In our model, because we started at half filling, that allows you to reduce the number of terms that you have, or the number of Slater determinants that you have in your states a lot. You find that for parallel spins there is only one term, such that there is no effective reduction of your hopping, and only for anti-parallel spins there is. If you include spin-orbit coupling already in this model, you will see that the effective hopping is reduced. And it can be reduced by quite a lot. In systems with open F shells, you can easily find that by fractional parentage, your effective hopping is a factor of 100 smaller than the bare hopping. That of course then gives rise to an extreme reduction of the bandwidth and therefore to effectively very heavy electrons. The nice things about such materials is that they become extremely susceptible to external stimuli. We also find that the fractional parentage can change with respect to the magnetic orientation between our lattice sites. If our atoms are perfectly parallel or aligned, we find that the electronic bandwidth is larger. So if we have a system with a few doped holes, then these doped holes will be at a lower energy when the spins are parallel, because then you can hop better and therefore they gain more kinetic energy. So once we have a lattice like this and we dope in a few electrons, you will find that the ground state becomes ferromagnetic, where all electrons align, or all sides align with the spins in the same direction. When you then increase temperature, you might overcome this order and the system starts to get disordered. The moment the system is disordered, the effective bandwidth will reduce, and it's then also introducing a disordered system where the hopping between sides varies between square root 1/3 pp sigma and pp sigma in a random fashion. Well, and we've seen before that for a random lattice you get an imaginary part of the self-energy, you get scattering times, so you get an additional conductivity, you can give the contribution to the conductivity, and the system turns into a bad metal. So what you find, and you do indeed find this for several heavy fermion compounds, is that At low temperatures you have good conduction. When you increase the temperature, you get a lot of scattering between the electrons. Your bands become incoherent and you go into a bad metal or an insulator. At some point it's maybe formally still a metal, but the conductivity can be so large that practically your system is just an insulator, which is what we then would call a bad metallic state. And that all because you have to fulfill the alignment of your electrons locally before you start to do hopping. So I've hoped to show you some of the effects that atomic multiplets, and especially the multiple part of the atomic interactions, can have on our materials and how this plays a role in different lattice models. And with that, I thank you for your attention. Stay healthy. We see each other later.